Hello community, so great that you are back. Now, in one of my last videos we were talking about here in-context learning plus. We were talking about ICL plus with DSPy, a self-improving machine learning system. We were talking about the discovery of new retrieval heads in our LLM, especially for long context. We were talking about here the ring attention mechanism for 1 million token context length, and I showed you the next generation of AI, like recurrent gamma, complete different architecture, but for long context length. And in the very last video, we discovered that the fine-tuning generates problems. And we talked about hallucination, and hallucination are just not correct answers. And we talked about here, if you have known training data in your fine-tuning or unknown data, the system behaves completely different. And we ended the last session, we ask here, is it better to have a supervised fine-tuning with a particular coherent adaptation to the pre-training knowledge of our LLM, or is in-context learning here the better approach under certain boundary conditions? And we ask for a specific, very specific LLM development. If you're a company, should you invest in supervised fine-tuning and DPO alignment, or not just jump directly into in-context learning plus? And today we follow this path and we say, hey, the number of demonstrations, these many short examples that we have in a prompt that can be provided for in-context learning approaches now the size of entire training datasets. So let's validate if this in-context learning is really happening at extreme scaling. We go here to the maximum length that we have available. Well, if I say we, unfortunately, I have to refer a study by Carnegie Mellon University at the end of April 2024, and they looked at exactly this, in-context learning with long context models at an extreme scale. And I read the study and I have to say, I'm disappointed. I'm disappointed that none of the global corporations like Microsoft, OpenAI, or Google Gemini with 1 million token length, or Anthropic with 200,000 plus token length, nobody seems to have provided here amount of money, amount of critical compute infrastructure for research. So we, the researchers, Carnegie Mellon, had to scale down here this extreme scale experiment and go for some basic models. And they started with a Llama 2 7 billion base model that has a context length of 4K. They looked then at the Llama 2 that was extended to 32K. And finally, another Llama 2 model for 80,000 token context length. So unfortunately, I have to say, we are not working here on the latest and best model from the global corporation. The corporation opened up their heart and their infrastructure and provided here research with unlimited access to a third-party university. No. So, okay, I'm disappointed, but let's go with what we have and see if we find some insights. Yeah, all these extended Llama 2 models, because Llama 2 we know very well, we know what works, what's not working. Llama 3 is rather fresh, it's not that solid yet. So, okay, we have to accept that we go with Llama 2. All this performed here the needle in a haystack style test and so on. Plus, we had not just to rely only on a Llama architecture, they also went here with a Mistral 7B version 02. That has here a focus on a long context window, and this means 32,000 tokens. Beautiful. So this is our architecture. Now to the data set that the researcher used at the university. We have 5 data sets in different domains: questions, conversational, financial domain, and clinical multiple. And you see the training size 5K, 5K, 20K, 10K, 15K. So those are the data sets that they use. They're a standardized data set. We know these data sets. So let's see now, depending on each of the 5 training data set, how each model does. So if we go here, yeah, you have here the 5 data sets, and here the accuracy. And if we go with the Llama 2, the base, you see, okay, we are in this particular behavior. But just if we go here to 32K, so an extended context length here, we're already here at the top, you see. So we have here performance from above 90% if we try to use here the available space. And then depends, but you see the 32K and the 80K, this top two here, sometimes they exchange their position, but they are here, yeah, they are quite nice. And of course, in whatever this is, pink, we have our Mistral performance. So you see, this is the general baseline that we will have and we will try now. Now the authors did 3 ways. They say, okay, so what we can do is we have a random sampling in context learning plus. So we just shuffle it around 10 times, the training data set, and then we average. And then across models and across varying number of demonstrations in context, they draw the first 1,000 examples, 3,000 examples from each shuffled data set. The second was, hey, if we have RAG, for example, we have a better solution because for each relevant query that we have, for each task, we can go in and we retrieve here only a relevant subset of examples. And we use here a specific retriever, a very simple retriever, to retrieve the most relevant demonstration by comparing here the test input text to the full demonstration text. So this means we do cherry picking. We just extract here the most semantically relevant information from our database, and we also bring those data that are very specific to our query back in our retrieval in context learning. And the third way, if you want, is the classical fine-tuning of a Llama 2 7B. We have done this for a month, so this is a stable system. We know how it behaves. It is not about the best performance, therefore we would use Llama 3. This is just to understand what happens in one class of LLMs, Llama 2 or Mistral, when we increase the context length. Does it really bring us benefit? Is it really operational if we go to extreme length, given here the limitations of those LLMs? And here we have it now. Now for the first set, the clinic, and then for the second example data set, let's look at this. So blue dots here are our retrieval, our very special retrieval RAG optimized in context learning data sets. And as you can see, they start really high because they're really computational intensive, pre-calculated to fit here optimal. But you see, they kind of plateau out here. And then, and this is the interesting part, we have our random ICL, no pre-selection at all. So we start here with 0 number of example in context here on the x-axis, only here. But look, we come up quite fast, and if we go here to 10 to the power of 3, so we have here 1,000 examples, you see we are almost here catched up with the perfect retrieval, semantically correct in context learning. So this is an interesting part. So we don't have to do the RAG. We can do with random ICL if the data are in this data set. And then in green, we have the classical fine-tuning of an LLM. So you see, it starts here. You need a lot of examples, but then it also goes up close to, let's say, they plateau out here at about 90%, and they're also almost there at 90%. So you see, it depends of the number of examples in context. If you take another data set, it's a little bit of a different behavior, and sometimes our fine-tuning can even become surpass in context learning if we have even more training data sets available. But that's it. Now, what we do not have, in my last video I showed you here this training accuracy when overfitting starts, and we saturate to 100%. When we saturate here to 100%, this happens because we have known training data in our fine-tuning here, in our green triangles. But there's also unknown data that they did not test for. So we have no information if those green triangles are more rather known data or unknown data. And you find more information here in my very last video on this. Anyway, now let's look at a number of examples in context. 10 to the power of 3, so 1000 examples is we have here that our retrieval, or perfectly retrieval optimized in context learning text, is on par with just a randomly retrieved in context learning. So beautiful. And you see here the performance of the fine-tuned model. If we go here, about 60% accuracy, and our other models are about 90% accuracy. So if you are in a data limited fine-tuning training set, I would highly recommend you go with in-context learning here. And you don't have to do here the RAG optimization on everything, because you see, even if you do a random selection of in-context learning from your training data, if you have the number of examples here, you catch up very fast here with the performance of a RAG optimized system. This is a very nice finding here of this study. Yeah, this is for another data set. But you know, I thought, if you look at this, and now this is 3 and 4, the number of the 5 data sets, you see the behavior is always a little bit different. And if you look here now, I thought, okay, but look, the retrieval ICL here, yeah, we start very high and we saturate here at, I don't know, 90%. Our random comes in from way down below, but comes up fast with the number of examples in context learning. And here at about 3000 many-shot examples in our prompt in context learning, we reach here about the maximum. And now I said, why they do not differentiate here between the Llama 2 80K or the 32K or the Mistral? Why is there just here across the models? So I would have loved if the authors would here also differentiated here, not only between the methodology of a retrieval ICL or a random ICL or a fine-tuned, but also show me here the different models with different context length, because this is what I'm really interested in. But okay, we only have what we have, but maybe it is hidden somewhere in the annex. So let's have a look. And there, I think Annex C1 or something like that, you find the data. And yeah, let's look at this. So the blue dot, now please, there's the same colors, but something different. So new color notation. The blue dot is here our Llama 2 base model, very old grandpa model, blue dot. And you see the blue dot goes up and up and up and up, which is amazing. So this means that the performance of the system goes up. The more number of examples, 10 examples, 100 examples, 1000 examples, we provide in context learning in one prompt. And then of course somewhere it ends with the 4K. And then we continue here with the 32K, and the green triangles is not fine tuning like in my last slide, but this now is here the 80K Llama 2. So you see we plateau here about 90% or whatsoever. And then we have the Mistral with 32K, and you see it has a similar curve, not identical, but of course it has a different training data set, a different pre-training phase. So you see for this particular data set, NLU, this is now the differentiation. Now I understand why in this slide they do not differentiate here further here the different context length, because somewhere simply one model stops and the other model with a longer context length continues and stops, and then the model with the longest context length, this contributes here with the most significant terms here. If we go up to 3000 many shot examples, now let's say, I don't know, every example has about, I have no idea, 1000 token, maybe only 500 token. So you understand why we come here to this thresholds. Beautiful. So this is a nice insight. Now, unfortunately, I wanted to see it myself. So I will say here, yeah, data and code coming soon. published 2 weeks ago. So yes, let's cross our fingers that we will get here the code and the data, that we can continue to work on these examples ourselves. Now, for the meantime, what are the insights? Now, understand that this is not really here the million plus token length, but we are here in a scaled down version. But I think even in a scaled down version, we got a characteristic of a system from a 4K to a 32K to an 80K token length. And we can answer the question, hey, is it working with in-context learning plus? With many short examples. And I think here the insights also by the author support, yes, it is working. So let's look at their insight. The performance continues to increase, as I just showed you, with hundreds or thousands of in-context demonstration examples. So for many datasets, this long context ICL approaches or even exceeds here the performance of models fine-tuned on an equivalent amount of fine-tuning data. And this suggests that as context length grow 1 million, 10 million, in-context learning can utilize this additional context effectively, making it a viable alternative to fine-tuning for certain applications. Now, this RAG-optimized, very close to a cosine similarity retrieved example, this example retrieval here, is highly effective in very short context length, 4K. But it offers diminishing returns as the context length increases, and does not really is necessary because it is time consuming, it is compute consuming, it is RAG consuming. So we don't need this if our context length increases even to 32K or 80K. Now, fine-tuning in particular datasets can surpass the long context ICL performance with significantly more fine-tuning data than ICL data. So fine-tuning is really more data hungry. So if you have almost unlimited access here to your training dataset, to your development dataset, to your test training dataset for fine-tuning, if it's in abundance, yes, okay, fine-tuning might be an alternative. So while the retrieval and the fine-tuning have their own strength, as we just seen, this long context ICL offers here a more balanced approach, particularly when computational resources or the data availability are limiting factors. Interesting to know. Now, understanding here the scalability of ICL Plus here with the context length contributes to the broader goal of developing here AI models that can handle vast amount of data without prohibitive cost. If you go today to OpenAI and you say, hey, I would like to use the GPT-4 base model and I would like to fine-tune this model on my company data, they will say, welcome. So we are talking about 10,000 plus to maybe 100,000 US dollars for the fine-tuning costs. So if you say, okay, maybe I start with a first prototype, maybe ICL Plus is a good candidate. But this depends on your task, on your data, on your financial portfolio, and so on. However, what I'm interested in is, can we use this in-context learning here for the improvement of the reasoning capabilities of LLM? Can I induce here in this 1 million, 10 million token length reasoning examples, many short examples, 1,000 examples of reasonings completely from step 1 to step 115 that the system is able to pick up without being fine-tuned on this. This is what I'm interested in, and more about this in one of my next videos. And I think there you have it. This long context ICL is less sensitive here to the specific order, for example, if you compare it here to very small short context ICL like 4K. However, careful, if you have a strong grouping, a strong clustering of same label examples, if everything that has the same label you put together, this still can have a negative impact. So distribute your examples and your different labels here very nicely across the available space. Whatever metric you take, it continues to improve here with increasing context length, peaking at hundreds or multiple thousands of examples, many short examples. So I think this studies, or the authors argue that it represents here a long context ICL as a viable alternative to fine-tuning our large language model. And it opens up some avenues here to understand or further develop models that can perform really well across some diverse tasks with some minimal retraining. So, an interesting study, a very limited study, because of the financial resources and of the, how to say this, competition between the global players to offer unlimited access to third-party university for some really dedicated testing of their models. Unfortunately, sometimes we have to rely on the corporation data that they publish themselves on their closed models. But yeah, this is the situation. So I hope I further develop this in-context learning with the extreme scaling on the data that we have to provide you a better understanding that in-context learning plus can be really an alternative to supervised fine-tuning. I hope it was informative. I hope you enjoyed it a little bit. And it would be great. And you know what?